So next we're going to talk about proximity networks, which are the ideal kind that you would want for cellular data. You can use them for a lot of different things, though. Anything that you want to describe using neighborhoods or just create a network between things just based on proximity. So once you do that, you want to start with your nodes here. Make sure they're labeled so they have different values, and then you would just go to process calculate network, calculate proximity network. You'll get this menu. The first one is the distance that you want the nodes to be able to connect to each other. So any nodes below the distance you enter here are able to connect. This is the most important parameter. The other very important one is going to be this one, which only applies if you're using centroids to do this computation. But you can tell it how many nearest neighbors you want it to connect to. So this will connect to the 5 nearest neighbors within 200 of your unit, of course, scaled based on these scalings if you want them to apply to real-world units. Here it tells it if it should use centroids. This is going to be faster, but may not be ideal for non-spherical objects. So in that case, you can also use morphological shape. And then there's 2 options for that, actually. The first one allows objects to connect to each other through other objects if the search region is large enough. And then this one stops that, pertaining only to the morphological shape, of course. The centroid can be done a bit more algorithmically, so you can just enter a desired number of nearest neighbors there. If you have identity set up, you can also tell it to create nodes only from a specific identity, so these are going to be right there. You can generate informative overlays here if you would like to. And so those are the main parameters you'd be concerned about. So let's run this here. And we're going to have to get our centroids, but as you can see now, every node is connected to the 5 nearest neighbors within the search region. And I'll show you what it looks like if we just don't do a limiter here and we just do the nearest neighbors. Of course, in that case, everything is actually going to get to its 5 nearest neighbors regardless of distance. So you have some flexible options there. So once you have this network, of course, like before, you can compute your network statistics. You get these histograms. You can use them to threshold nodes to pick out like high scoring ones here or whatever you want. There's some other cool stuff now that you can compute, like these nearest network neighbors. You can find the shortest path here between your highlighted nodes, and this also can do it through identities. So for example, here's the shortest path through these nodes here, and we also made a heat map, which is telling us that these are kind of far apart, and these can be computed between any 2 specific identities, which I mentioned, but what you want to do with these proximity networks usually is it's good for cellular data. So let me show you what I'm talking about. Yeah, so let's start with this, and I'm just going to clear these out. So here we have a set of segmented cells. This comes from a tonsil, which is kind of like a lymph node. So they're very dense with immune cells here. And I can kind of show you some of the other channels. So when you're doing this, you would want to take some channels with your image to describe different properties. The more channels, the better, I'd say. But here's SMA, which is sort of an actin stain, so it's picking up mainly blood vessels I'm seeing. You can see that cells that overlap with these stains, we would consider these SMA positive, and so the question is, how do we assign that so that we can appraise these cellular neighborhoods based on that? Well, the way you would want to do that is you would start with your segmented nodes that you segmented with cell pose or whatever in your nodes channel, and you go to this function here, assign node identity from overlap with other images, load that, you get this menu. And then what you want to do is you want to take all the channels you're interested in and put them in a folder together as TIFFs. So you would not have a single large multi-channel image in one file. You want to separate out your channels in a folder. You could do that with something like Fiji or ImageJ. So I have all my channels here, and I have a subset here just to demonstrate what you do here. And then you have some options. You can make your nodes just step out a little bit with their search for when they find if they should overlap with identities or overlap with the channel. But we don't have to do that. This is mainly if you had a nuclear segmentation, but this one actually does use cell membranes, so I'm just going to stick with what I have. The strategy here, you would probably do this your first time doing it. You have two other options here. This is going to be if you train an ML model, you can have it automatically predict all of them, or you can use previous thresholds if you're just reapplying on the same data set or a similar one. And this last one is just mainly if you binarized everything yourself, but I would probably go with this one because this is kind of what this is designed for. We can tell it we want to train an ML model also, and then when you're ready, you would find your folder that you put this in. And so here's my folder. Make sure that there are no other channels that you don't care about in here. You only want, at least regarding .tiffs, for them to be the channels you're interested in. You can have other files, those don't really matter. And then once you choose this, it will do some processing. It's computing the average intensity for each cell or each node. And then it's going to want you to save that spreadsheet. I already did this one, but I'll just resave it just to sort of demonstrate what I mean. This spreadsheet is important because you use it for some calculations down the line, so don't forget to save that, or you'll have to recompute it. And at this point, it's going to interactively load each channel one at a time into overlay 1 here. So I'm looking at TCF1, and you can see there's some bright cells that I might consider as valid expression, and then these darker ones probably not. So what I want to do is I want to use this histogram thresholder here to pick up the cells that I'm defining as real and make sure that it's not picking up the ones that I don't like. So I think like around here is what I would consider as like a baseline valid expression for this marker. So I'll continue with that. Here's the next one. And because these channels have inherently different brightnesses sometimes, you might have to change around the brightness here. But we can see like here and in these germinal centers, they're strongly expressed for tox. So you would want to move this until it's getting everything you want. And then you do that for the next few also, and I'll just skip through these quickly. Usually you're going to be kind of on the right side of your histograms when you're doing this. And then when it's done, because we opted to train a model, it's trying to save the model. I already saved it, but you would just save it here. And then when you're done, you will get your node identities. So your nodes now will bear identities based on the assignment you did. So here's like a Vimented positive, and then some of them have nothing if they just didn't overlap with any of those markers. And just real fast, I'll show you what the automated model version looks like. So we can load our model that we trained, and now if I process this, once it's done the same pre-processing, then we get here, and you can actually use the model to predict, your bounds, and you can see it's sort of replicating what I did because it was trained on this data set anyway. But if you had similar looking data sets, similar modalities of imaging, and you trained it on a bunch of channels, then this would be a good way to be able to automate the process down the line. And of course, if you load the model, you can use this if you're comfortable and have it just do all of the thresholding for you. Skip that completely. You can also load like your spreadsheet if you want to add more channels. You can load what you've done so far to skip the pre-processing. So there's like a few different ways you can use this menu, but the main idea is that you're assigning your node specific identities. So I'll go to the master folder for this data set, which is here, and this one I've already done for all 70 channels. And so I'm just going to go through some of the steps to do analysis on cellular data. So let's talk about creating neighborhoods. And I've already done this on this, but I'll just demonstrate it again. So like we already did, you would want to calculate a proximity network. You can set a limiting maximum distance and a number of nearest neighbors. I usually just do 20 as a good default for these sort of cellular analyses. And now you'll get here, and the network has been computed. So if you see, if I click on any node and I show its neighbors, it's picking up its 20 nearest neighbors. So each cell is sort of aware of its neighborhood now. And what we can do is we can take those neighborhoods and cluster them, cluster the ones that look similar together to sort of describe different motifs in the tissue. So previously we talked about, calculating communities with network dynamics, but now we'll calculate them based on neighborhood composition. And so you'll choose that second community grouping option. And all you need to do now is enter a number of communities. If you want, you can enter a number of minimum neighbors and node needs. And then these options are for computing the proximity network if you haven't done that yet, which I already did. So you don't necessarily need to do that if you've already done it. You can also generate a UMAP, which can be interesting, although it might be slow on really big data sets. So just be aware that it might freeze your computer. This is a lot faster up here. So if you're just interested in the communities, you'd probably do this, save your file, and then try to generate the UMAP a second time, and see if that does it in a reasonable time frame. But I'll show you what it looks like here. So we'll just create our communities here. And you'll see the loading here. It will compute the communities a lot faster than UMAP. So now it's on the UMAP already, and this is probably going to take like 10 times as long as the communities. So our community has been assigned, and we also created the UMAP. One thing you can do is you can use this to show your communities in the overlay as a color schema. You'll get this legend just to help you out. And as you can see, these communities appear biologically meaningful. We have our germinal centers quite apparent. We have the mantle around the germinal centers being picked up as an independent thing, paracortex around that, and then we can also see blood vessel specific communities in this pink and red one. So the pink is more like internal blood vessel structures, endothelium type thing, and then the red is going to be more around it, so possibly like muscularis type tissue. And then we have our UMAP here. So the UMAP's actually interactive, which is neat. So what you could do is you can circle areas that you're perhaps interested in. You can see on this UMAP, these are our germinal centers, clearly quite distinct from the rest of the tonsil. And once you select stuff, you can, if you desire, assign it to its own community or to a new identity from here. These UMAPs can also be saved and reloaded with this button if you don't want to bother computing the embedding every single time, which I recommend. So once you have communities, one way you can easily describe them is go to Network, Calculate Composition of Communities, and just hit this with the default settings. As you can see, we get two heat maps. The first one describes the proportional breakdown of every community, so you'll see like 0.1 as a value. That means like 10% of the community is that thing. So here we're looking at this. These nodes can have multiple identities, so these won't necessarily add up to one. And this can be used to describe like what kind of tissue a community is. And then the second one is more of a relative expression, so values that are more abundant in a community versus the entire tissue become more red and get a value greater than 1. And also less than 1 if they're underrepresented. And you get this heat map here. You can save both of these, export them as CSV. A rapid way to analyze your cellular data then would be to do this pipeline that I've shown so far, and then save these both. And then you can show your CSV to something like ChatGPT, ask it based on the first one what type of tissue it thinks the community is, and based on the second one, look at what cells are enriched, what perhaps rare cells are enriched there, and what that might mean that's interesting to the tissue or the analysis that you're doing. So that's how you would do it with the supervised thresholding. Another option is to do more unsupervised clustering. So if we click on this menu, let me just show you the menu again. Here under stats, show identity, violin, UMAP, assign intensity community is kind of a mouthful, but you would want to click on that. And then find your spreadsheet from earlier. This is the one we saved for that demo, but I am just going to find the one with all of the channels and load that. and here you'll get your spreadsheet. You'll get this menu. And so the first options, you can describe specific identities in the relationship to other channels, and also communities using violin plots. If you click this, so here we're looking at the overlap of other channel markers with our CD20, which is a B-cell stain. So as you can see, CD20, everything is above 0. This lower boundary is based on what we defined in our thresholding as the lowest boundary that we considered valid for that cell. If you didn't do the thresholding and you just brought the spreadsheet straight here, this lower bound will be based on medians for the distribution instead, which is a bit harder to interpret. But if you did define, you could say, oh, everything that's above the line is what I, as the user, would characterize as valid expression. So we can see our CD20 in this sample is often co-expressed with CD3, co-expressed with the CD45 stains, co-expressed with the CD16 stain, but everything under it is going to be less expressed. And same idea with the community. So here's community 1, and community 1 has a lot of CD16, a lot of CD3. So if we look at what community 1 is, we can see it's like this region here, and this one actually doesn't show much of the CD20, which is probably going to be mainly in the germinal centers. So you could see that this is a more visual and more community or identity focused way to break down your tissue than using the heat maps that I showed before. You can create UMaps here directly from the intensity data. Everything here is going to be z-score normalized essentially, so you don't have to worry about odd differences between the distributions. And one way that you can utilize the heat map here is for these three, you can go to this plan identities menu, and this will control what identities are showing up on your heat map. If you label it by identity, you can also label it by community, and it controls which ones show up in the violin plots also. But you can also do this heat map identity menu. So let me show you how this works. So what you want to do is select markers that you would want your cells of interest to have. So I'll do CD45, I'll do CD7, and then ones that I don't want it to have, I'll do CD3. And so this kind of loosely describes what a natural killer cell might look like. There are some more other markers that natural killer cells might have, but this is just sort of a broad way to describe them. And then if I generate my UMAP, since I'm labeling it by identities, you'll get this menu. This menu also comes when you click on this here. So the UMAP, when you're labeling with the heat map, will call this method. So just think about this method as doing this, but not showing the resulting UMAP. But you'll get a thresholder, and I'll show you what that's like. And you can weight these also to make the presence of these markers more impactful or the absence of these markers more impactful. But by default, they'll just be 1, and I'll show you how 1 works out. Okay, so just starting out, we have this thresholder, and this is what you would get if you just press this menu, but it also will show up if you do this heat map UMAP. And what this is doing is it's picking out the cells that most resemble this sort of mixture of markers. So it's finding them mainly in the paracortex, which is kind of what you'd expect from a natural killer cell. And then if we look at our UMAP, and let me just unselect these highlighted nodes, just so we can see the heat map better. But we can see 3 distinct communities that resemble our mixture. So on the top left here, let's circle this. And we can see this is going to be the paracortex region. And then we have some other candidates here. And these ones are just scattered throughout the tonsil a little bit. So it might be the ones in the paracortex are sort of like more resting, where these ones are more active and are probably trying to leave the lymph node or the tonsil. And that's kind of how you would use that in general. And like before, you can save your UMAP if you don't want to bother recomputing it, because it can be a little bit slow. And then besides just that, we have some clustering down here. So this is going to be clustering based on the raw z-scores and not your thresholding. So it's going to be less supervised, but for one, it's going to be faster because you won't need to do the manual work, and it will be, I guess, less prone to operator error. But I do like to do the thresholding anyway, just because it's useful for some analysis, if you can. But if you wanted to just do it quickly, you could do it like this. And then you have two ways to describe it. This describes the neighborhoods based on the network. This will look at the breakdown of individual nodes. So let's just run it on the individual nodes really quickly for 10 communities. And we can get this heat map. This is a little different than the one that describes the communities. This heat map is describing the average z-score for the expression of each marker in each community. And this is a new set of communities we just created, so I'm going to recall this function just so that we can see them. And as we can see, these ones are describing individual nodes, so they might be describing cell types more so than neighborhoods. For example, you can see in yellow what appears to be endothelial cells quite distinctly around this blood vessel. And then, of course, if we have a proximity network set up, which we already calculated, we can do that for the proximity network, sort of similar to how we were doing neighborhoods before, but without supervision. And here is the results of that. So they're all like a little different from each other, but they do describe slightly different things. So you would just want to tailor it to your use case. And then, of course, when you're doing your analysis, you always want to save your session so you can come back to it later. Now, when you save your session, you just enter a folder, save that, and then you can drag the entire session folder back into the image like I did earlier when I loaded this one. Okay, and then lastly, I just wanted to really quickly show how you might use this in a 3D data set, especially one that doesn't even have cells in it. So what you can do is, here's an SRS data set, which is Raman spectroscopy. The IR wavelengths help you pick out different areas of tissue that are expressing a metabolite. So here's a protein marker in a slice of kidney, and this was imaged slightly deep, so we can see through the stack. Now sometimes when you have these 3D images, and I'll just pull up the raw here, but when we take a look at this, we can see that deep in the stack, it's actually getting darker. And this is bad when we're doing intensity-based comparative analysis, because we don't want it to be, dark down here and then have it not pick up anything down there. So what you can do is you can actually normalize your channels if you go to this normalize brightness method. And you can just run that. It wants you to threshold out your background. This is optional, but if you did have a background, you would not want that being considered. So just move this slice until it's picking up only the actual tissue. Here there are some holes in the tissue, so you might consider doing that, but I'm just not going to do it for this case. The background is already thresholded out, I should mention, the actual background that's not within the tissue itself. So you would not want to include any truly empty region where there just wasn't something on your slide, so you would want to threshold that out, and that's kind of what that's asking you for. But otherwise, it'll process on whatever your active image is. And this might be slower if you have a big image, but it normalizes the brightness across all three axes. So you would want to normalize it, therefore, for all channels as needed. So you can see I have all my channels in this folder, and they've all been normalized. If you don't need to do the normalization, of course, you can skip doing this. I mean, don't bother with it if you don't need to. But once you have this, this is my image here, and we don't have cells, so you might wonder, what do we use as nodes? Or maybe you do have cells and you don't really care about them. Well, one thing you can do is you can go to generate, and then do generate artificial hexagonal nodes. Click on this. You'll get this menu. If you have a 2D image, this can create hexagons of an arbitrary size to serve as artificial nodes that kind of tessellate through your image. But you can also use dodecahedrons or prisms. for 3D images. So the dodecahedrons are a bit more 3D tessellators, and the prisms might be better for short z-stacks like this one. So I'm going to go with the prisms. I'm going to create hexagons of side length 8, and if you click this, whatever is in your nodes channel, it will restrict the hexagons only to be in the positive regions. So because we thresholded out our background, we're going to only create hexagons here, and I'm just going to run this now. And it's already done, so I'm just going to swap this into my nodes channel really quickly. And now, as you can see, when I click on this, we have hexagons. And when I, you can see that these hexagons have depth to them also. So it's going to be a true 3D structure. And I've already done this, so let me bring this in with the nodes that I used before. I guess that image had some holes in it, but here's what they look like otherwise. And like before, you would, from these hexagons, calculate your proximity network. So, you can do 20 as nearest neighbors. And then I'll just load this in so we have the proximity network anyway. But yeah, here we are with our hexagons. We have a network, so if I do, let me just go to like some hexagon. If I do show neighbors, you can see each hexagon is linked to its neighbor, and it's linked in the z-stack, which is a bit shallow, so it's branching out seemingly more, but these are actually the same distance if you look at the scaling. And similar to before, we can do the thresholding on our channels. Of course, you'd want to save the resultant spreadsheet like usual. Okay, and so like before, we have our channel in our overlay 1. We can scroll around and use this thresholder to select what we want included. And so we would just do that for every single one. It's the same idea that we did before, but now it's going to be in 3D. So when we look at our objects here, you can see each one includes this set of markers in the 3D space using these hexagons. And then what we get from that is we can create neighborhoods like we previously did, describing these regions. Same idea as before, so you describe them with the Analyze menu. Like before, you could use this menu and load your intensity spreadsheet and create communities that way, or do any of the other stuff that I've already shown. Yeah, and that's basically that.